All right, so continuing on our discussion of the types of chemical reactions, we've looked at synthesis, we've looked at decomposition, we've looked at single displacement. It's now on to double displacement. Okay, and then we'll do combustion and we'll do redox later. So double displacement reactions. In general, you're going to have two compounds that are going to switch a piece of themselves. Okay, two ionic compounds, they'll be in solution, aqueous, and they will switch their cations, their positive ions, to form two new ionic compounds. That's how it works. Okay, so the reactants are always two aqueous ionic compounds. The products are going to be two new ionic compounds. Well, two new compounds. At least one of them has to be a solid, an insoluble precipitate, or a molecular compound like water or a gas. Okay? That's the requirement. So for a double displacement reaction to occur, one of the two products that you form has to either be a precipitate or a molecular compound. How are we going to figure that out? Well, we'll have to look at some solubility rules that will help us figure that out. Now, double displacement reactions are also sometimes called metathesis. You might see that in a book. It's an older term for this, but that's what it means. Okay? All right, so here are some examples. I want you to jot them down in your notebook and leave some space so that we can write some equations and balance them. Okay, we have solutions of lead 2 nitrate and potassium iodide mixed together. We have a solution of sodium sulfate added dropwise to a solution of barium chloride. And we have a carbonic acid solution neutralized by adding lithium hydroxide, which is a base. Okay? So write them down, leave some space, and we'll write some equations. Okay, so for our first one, we have lead 2 nitrate solution and potassium iodide solution. I'm going to write my formulas fairly quickly because by now we should know how to write formulas. If you don't, go to my YouTube channel and watch the videos on formula writing. Lead 2 nitrate, Pb, NO3, 2, and that is a solution, aqueous. Potassium iodide, Ki, that is also a solution. What's going to happen is the lead and the potassium are going to switch places. Okay? Now, they're different charges, and when I write my product formulas, I need to take into account the fact that potassium is +1 and lead is +2. Okay? So when lead goes and switches places with potassium, the lead will go with the iodide. Iodide is -1, lead is +2, so I should write PbI2. The potassium is +1 and so is nitrate. Nitrate is -1, so I should write KNO3. Do not get thrown by subscripts that might be showing up on one side or another that don't seem to match. Okay, I have a lot of people who want to write PbI here because they don't see a 2 after the I over here, so they don't put one over here. But you have to, because when Pb +2 goes with I-, it has to be PbI2. We'll take care of the numbers when we balance, which we're going to do right now. We have 2 iodides. We only have 1 on this side, so I'm going to put a 2 in front of that. That gives me my 2 I's. That gives me 2 K's, so I have to put a 2 there to get my 2 K's. That gives me 2 nitrates, which I already have over here. So now it's balanced. Now, I didn't put in my state symbols because I'm not really sure yet how to do that. I need to learn my solubility rules. So we'll come back to this one. The next one is sodium sulfate and barium chloride. Sodium sulfate, Na2SO4, aqueous. Barium chloride, BaCl2. Again, if you don't know how I got these formulas, go back and watch the videos on formula writing on my YouTube channel and figure it out. Okay? Sodium +1 is going to switch with barium +2. That's going to give me a couple of different formulas here. Sodium will go with chloride. Well, that's NaCl. Not NaCl2. There's no such thing as NaCl2. Yeah, but there's a 2 over here. It doesn't matter. We'll fix it when we balance. Na +1, Cl -1 has to go together like that. Okay? Barium +2, sulfate -2, BaSO4. Okay? To balance, I'm going to need a 2 in front of the NaCl to get 2 sodiums and 2 chlorines. There's my 2 chlorines, there's my 2 sodiums over here. So now it's balanced. Again, no state symbols until I know my solubility rules. Let's do the last one. Carbonic acid. Carbonic from carbonate. Carbonate is CO3 with a -2 charge. So H2CO3 is carbonic acid. Acids are always aqueous. Lithium hydroxide. Li +1, OH -1, LiOH. Now, what are we switching here? The cations. Well, the cation in an acid is always H+. So the H+ is going to switch with lithium, which is +1. H+1, and lithium plus 1. H plus, when it goes with OH minus, forms HOH, which is also known as water, H2O. Li plus 1, when it goes with CO3 minus 2, has to be written Li2CO3. But there's no 2 after the Li there. It doesn't matter. It has to be when I write lithium carbonate. So now I have to balance. Well, I need 2 lithiums over here. So there's my 2 lithiums. That gives me 2 hydroxides. Well, each water molecule contains 1 hydroxide, so I'm going to have to put a 2 there. And that'll give me my other 2 hydrogens, 1 carbonate. Again, no state symbols until I learn my solubility rules. Well, you know what? Let's learn our solubility rules right now. So, in general, we want to get a couple things straight. If a compound is soluble, if it dissolves in water, that means it'll exist as an aqueous solution, AQ. If it's not soluble, it won't dissolve, it'll stay solid, and we call those precipitates. Remember, in a double displacement reaction, at least one of your products has to be an insoluble precipitate, or a molecular compound like water, or a molecular gas like hydrogen or fluorine or chlorine or oxygen, any molecular compound that's not going to be aqueous. It's going to be solid, liquid or gas. Okay? So in order for those reactions to be considered to be true reactions, one of my products has to meet these conditions. All right, how do we tell if something is soluble or insoluble? We use the solubility rules. There are a few. You have to know them, as in memorize them. First one, alkali metal salts are always soluble. Anything that contains lithium, sodium, potassium, rubidium ions, it'll always dissolve. Easy enough, right? Anytime you see an alkali metal, it's soluble, aqueous. Ammonium, anytime you see an ammonium ion, it's always soluble. It'll be aqueous. Anytime you see nitrate in a compound, it will always dissolve. These 3 will get you through like 90% of your solubility. This is using these 3 because they show up all the time. Okay, so anything that contains an alkali metal, an ammonium ion, or a nitrate ion will always dissolve. Okay, now we get into a couple of special cases. So halides, chloride, bromide, iodide. Generally they will dissolve unless they are paired up with silver ions, lead-2 ions, or mercury-1 ions. If a halide is paired with one of those, then it will be a solid. It won't dissolve. It'll be insoluble. Okay? Sulfates. Anything that's a sulfate will usually dissolve unless it's paired with one of these 5 ions: barium, strontium, calcium, lead-2, and mercury-1. All of them are +2 ions. Okay? So other sulfates will generally be soluble, but if it's with one of these, it will be a solid precipitate. Hydroxide salts, anything that's a hydroxide will be insoluble unless it's with an alkali metal, obviously, because all alkali metals are soluble, all alkali metal salts. And if it's with ammonium, it'll be soluble. But if it's with barium, calcium, or strontium, it'll also be soluble. It'll dissolve. Okay? Anything else you can consider to be not soluble. All right, so write these down in your notebook because we're going to apply them to the examples we just did to figure out if we in fact have double displacement reactions and what our physical states of our products should be. All right, here was our first example: lead-2 nitrate and potassium iodide to form lead-2 iodide and potassium nitrate. Well, potassium nitrate not only contains the nitrate ion, but it contains an alkali metal ion, potassium, which means it's always going to dissolve. It'll always be aqueous. What about lead-2 iodide? Contains the iodide ion. Iodides are usually soluble unless they're with silver, lead-2, or mercury-1. Well, this one is with lead-2, which means this is not going to dissolve. It's going to be a solid. So there is my precipitate. Okay? It's a solid that has formed out of a solution. Sometimes we abbreviate PPTE. Okay? 2 clear colorless solutions will produce a yellow solid precipitate, and then this clear colorless solution. So we've produced our solid, therefore this is a valid reaction. Let's look at the second one. Sodium sulfate and barium chloride. We have sodium chloride and barium sulfate. Sodium chloride contains an alkali metal, which means it's going to be aqueous. It dissolves. Barium sulfate. Well, sulfates usually are soluble unless they're with one of those special cases, one of which is barium. The barium ion makes this solid, insoluble. So there's my precipitate, PPTE. Okay? So this is a valid reaction because one of my products is not aqueous. Final example was carbonic acid and lithium hydroxide. Well, water is not an ionic compound, even though we can kind of sometimes think of it as being made of ions. That should be H+, by the way. It's not really made of ions. It's a molecular compound, and it's a liquid. So there's a non-aqueous. We've met our requirement. What about lithium carbonate? Is lithium carbonate soluble? Well, it contains an alkali metal, so yes, it is aqueous. So at least one of our products is not aqueous. This is a valid reaction. Okay? So it takes some practice. You got to learn those solubility rules, and you got to get used to using them. Like I said, 90% of the time, the first 3 rules will take care of business. But if they don't, you got to know the special cases of the other ones.